We are watching a live, high-speed terminal stream next to a web dashboard. The left side logs rapid state updates, while the right traces a continuous ECG waveform, right up until the moment it flatlines. The human body operates as a distributed network of autonomous microservices. It is not a single cohesive machine governed by a master script. To prove this, we built the DigitalHuman project. It is a biomimetic simulation written entirely in pure Python 3.12, utilizing zero external dependencies. The foundational architecture breaks human physiology into 15 major organs. Each organ runs as a completely independent asynchronous task. These organ tasks share no memory and hold no direct references to one another. They communicate exclusively by pushing and pulling data through 3 distinct message buses. Because of this isolation, the simulation naturally produces emergent system failure and physiological homeostasis. There are no centralized, hard-coded rules telling the body how to balance itself or how to die. Most software relies on a central controller dictating global logic. This simulation relies strictly on localized resource consumption constraints. Each node is only trying to keep itself alive. Asynchronous message passing is what governs the complex interactions between these nodes. Organs broadcast local state changes, and the network reacts. Modeling human biology through pure asynchronous architecture gives us a perfect programmatic blueprint for building emergent complexity. Look at this diagram. Before we instantiate an organ, we lay down 3 parallel lines for communication protocols. The top line is the bloodstream bus. We treat this as a shared state dictionary where variables continuously update. We implement this data exchange using arterial and venous async queues. Organs pull required inputs from the arterial queue and push waste outputs back into the venous queue. The middle line is the nervous system. We structure this as a multi-channel, high-frequency pub-sub bus. Organs subscribe to specific signal types. When a broadcast fires, async callbacks trigger immediate, localized reactions without blocking the main event loop. The bottom line is the endocrine system. This operates as a slow broadcasting state mutator, using negative feedback loops to incrementally adjust persistent variables over time. We have shared state, high-speed pub-sub, and slow broadcast. These 3 distinct messaging patterns provide the complete communication infrastructure required for biological autonomy. With the buses in place, we create the organ base class. All 15 biological nodes inherit from this schematic. We enforce a strict object-oriented rule. No organ holds a direct reference or pointer to another organ. Inside each asynchronous task, a run loop executes continuously, tracking a localized health integer that starts at 100. The loop mandates a consume resources function called every cycle. To survive the cycle, the node must successfully pull a threshold of oxygen and glucose. Failing to pull required oxygen triggers localized hypoxia damage, deducting points from its health integer. This damage degrades the organ entirely independently of the rest of the body. Systemic biological vulnerability is simply the mathematical accumulation of localized resource starvation within isolated event loops. When we initialize the system, the boot order intentionally mirrors human biological development. We instantiate the brainstem first. It boots up as the foundational autopilot daemon. Every 0.43 seconds, the brainstem pulls the shared bloodstream bus for current CO2 levels. Based on that math, it calculates a respiratory rate and publishes a respiratory drive signal to the nerve bus. Next, we start the heart task. It acts as an intrinsic pacemaker, looping every 0.08 seconds to update blood pressure metrics independently of the brain. Then we instantiate the lungs task. This introduces our critical architectural dependency. The lungs lack internal pacing. They will only execute their gas exchange logic upon receiving the specific respiratory drive event from the pub-sub bus. Breathing is not a global biological state. It is a strict publisher-subscriber dependency between 2 isolated daemon processes. We test the simulation's flexibility through the pharmacology system, injecting dynamic external variables into the live loops. We use epinephrine as the test case. It functions simultaneously as a powerful vasoconstrictor and bronchodilator. The command executes exponential decay over time. When the drug parameters hit the bloodstream bus, the heart node reads the change and instantly pushes its intrinsic rate up by 40 beats per minute. Simultaneously, the lung node reads the same blood state and responds by mathematically widening its internal airway diameter parameter. Because the heart is beating faster, total oxygen consumption increases dramatically. We achieve this without ever toggling a hard-coded fight-or-flight global variable. Complex physiological reactions are actually just parallel, localized parameter updates decaying over time across independent nodes. The ultimate test of this distributed model is executing the kill brainstem terminal command. When executed, the brainstem terminates. The nerve bus stops receiving respiratory drive signals. The lung task hits its timeout and halts gas exchange. Without oxygen, the remaining organs trigger a severe drain on the O2 budget. Once the shared O2 level drops below 40%, the brain node registers extreme hypoxia. It begins subtracting consciousness integers at a rate of 10 points per cycle. In parallel, the heart node continuously fails its resource checks. It takes localized ischemia damage, dropping its internal health integer until the task fails. When cardiac output hits zero, the background death monitor daemon pulls the empty state and halts the entire application. Death in this model is never a scripted sequence. It is the inevitable mathematical collapse of decoupled asynchronous loops starved of shared resources. The entire DigitalHuman codebase does not contain a single line of logic explicitly deciding how to die. Traditional procedural programming relies on brittle, centralized exception handling. This simulation models the emergent reality of true distributed failure. Look at your own software architecture. When your systems fail, they rarely fail because a single master loop crashed. They fail through localized resource starvation and missing pub subdependencies. The most robust, highly complex software architectures can be achieved by actively mimicking the strict, decoupled constraints of human physiology.